Microscopic Ohm's law. Microscopic Ohm's law, this is different from macroscopic Ohm's law. The expression for voltage which is given by V is equal to IR, where V is the voltage, I is the current and R is the resistance. That equation is known as macroscopic Ohm's law. Means that equation represents macroscopic Ohm's law, but I am talking about here in this video microscopic Ohm's law, which is given by this equation. J is equal to sigma into E. J is equal to sigma into E, where J is a vector quantity, E is also a vector quantity. J is current density, means it is amount of current per unit area of the conductor. And of course it is a vector quantity. Okay, and it is expressed as ampere per square meter. Next comes, in the right hand side you can see E is there. E represents electric field, which is expressed as force per unit charge. Okay, and unit of that is volt per meter. Okay, and sigma is there, that represents conductivity of the material, means it is material dependent. Okay, so sigma, this is expressed as Siemens per meter. So this is equation for microscopic Ohm's law. But here this sigma, this can be expressed as N into Q into mu, where mu is the mobility of the charge carriers. Mu is the mobility of the charge carriers. N is the number of charge carriers per unit volume, and Q is the charge of a charge carrier, means electric charge of a charge carrier, that is denoted by Q. Okay, so this makes sigma. N into Q into mu is sigma. So you can see that these properties you will find at the microscopic level. Since these properties represents microscopic properties of the conducting material, that's why this is called microscopic Ohm's law. Okay, but in case of V is equal to IR, there you can see there is absence of microscopic properties. No microscopic properties are there in the equation V is equal to IR. But in this equation, you can see microscopic properties are present. And that's why this is called microscopic Ohm's law. And you will find the use of this law or use of this mathematical expression in the field of semiconductor physics, where electrons are moving, holes are moving. Okay, and this movement depends upon the electric field and the property of the material. So for the design of electronic circuits, this law is necessary in the field of semiconductor physics. Again, in the field of nanotechnology, in the field of material science, this equation is required. This equation itself expresses few microscopic properties of the material, conducting material. Anyway, so this was all about microscopic Ohm's law. Okay, this is very simple. You can see, very simple. And macroscopic Ohm's law, that is also very simple. That is very easy. Okay. Anyway, so this was all about the topic microscopic Ohm's law. Okay, so this is the end of this video. Thank you. Thank you for watching this video.